you suck at interviewing and you're not going to get any better. Oh, just kidding. Cracking the coding interview is one of the best resources for learning. I call it level 1 because it's a great start if it's been a while since you've taken a data structures class or slept through it the first time like I did. So go ahead and grab that in the link below. Oh, what's that? Also grab elements of programming interviews. It's a lot harder, but you'll be well prepared if you know it. Link in the description below. All right, this is Leetcode number 146. Least recently used cache. Given a cache with an initial capacity, implement the get and put operations. So, for example, this is a cache, which is in this context is another way to say a map. So there'll be keys and values. So say you were to initialize your cache, new LRU cache with an initial capacity of 2. So say you put in, 1, 1, key value 1. You're fine. And then let's put in 2, 2. And then let's do a get at 1. That will return 1. But now when we put in 3, what implicitly happens is that now that we have 3 items, one of them has to go, and it is the least recently used one. So put just got used, get just got used, so now 1 should be evicted from the cache. So a get at 1, 1 would return null. Additionally, if you were to do a put at 3, 4, that would just update this value and not increase the capacity. But yeah. So if you're doing this in Java, there's actually a way to do it with the built-in library. There are 3 types of maps. There's hash maps, tree maps of ordering, and then there's also like a linked hash map, which maintains an insertion order. And that has a function called remove eldest entry, which would be exactly what we're looking for. But that's not really the purpose of this question, to test your library function knowledge. So let's see how we would do it. And the way we're going to do it is actually the same that the Java standard library does. So that's kind of a vote of confidence. Anyway, what do we need? So if we're shooting, and just to say we're gonna have put, into key, into val, and also get. These are the functions we're implementing. So, and both in O of 1 time. So we know we're going to have to store keys and values, so that suggests a map. So let's say we store everything in a hash map to start. So we'll have our hash map. What other variables might we need? Probably to store our capacity, probably a count of how many we have currently. And then we have to figure out how we store the ordering of these keys. So you could say, okay, a list. Say for that last example, we had a list of 1, and then we put in 2, and then we get 1, and then it starts to fall apart. An array won't work because of how we're reordering it, and the size might change. So maybe we could do a linked list. So we had a head node, and a 1, and a 2, which is a step in the right direction. Let's look at what happens when we actually do a put. So specifically this put. So say we already have 1, 1, and 2, 2 in our hash map. Say we had a list of 1, 2, and say this was head. Say for this purpose that we're always inserting for new items. Every time we do a put for a new item, we're inserting at the head. Inserting new items at head. Well, for like a get, for example, we'd have to potentially go through the whole list. So say we said like get 2. Then we potentially have to go through the entire list and move that to the head. So that would make the get operation an O of capacity runtime object. So that's not great. So what else could we do? Well, instead of how about this? So instead, we need a way, because when we actually are getting, what are we doing with our list? We're doing a lookup, so like a search, and then we're also doing a delete. And if those both need to be constant time, we're probably thinking about we need another hash map or something of that sort. So in our initial hash map that we were going to store of the values, how about instead of storing an integer mapping, we store a 1, like the same key, but instead of a value, we have a node class with our value. Let's see here, and then we'd have probably a next and also a previous. And I say these next and previous fields because with this way we'll have a reference. So say we wanted to remove 2, we'll be able to easily look up 2 and remove it. But say we wanted to remove 1, we would find it in the hash map, we would find the node, and if it was singly linked, we'd be able to remove it, but it would also half the list basically. So say we had a doubly linked list. That's easy because we have pointers to each side, to the left and the right, and it's very easy to delete. So to summarize that part, we're going to store everything in a map, and then we're also going to store the ordering in a doubly linked list. So that would be O of 1 put, O of 1 get, and then O of capacity extra space. So let's see how that'd look like in code. I'm going to start by implementing the node class, and then I'll get to the actual cache. So just checking that we're recording. Cool. So we'll need a node class. So, and what's in there? So we have the sorry, I'm just pulling up my notes. Okay. We'll have our key, we'll have our value, and then the left and right. So node left, node right, and that's our linked list. It's as simpler, like that's it. We will need to add a few methods to support it, but what might those be? Well, whenever we do a put, we'll have to add a node to the beginning. So let's say private void add node. And all this is going to do is just add a node to the beginning of the list. Add node to beginning. Also, we'll need to remove nodes. So given a reference to node, we'll need a way to cleanly remove that. And then our third operation will be called during a get. So what happens when we get an entry? Well, it makes it the most recently used. Essentially, we have to change the ordering. So because we're adding new items to the beginning of this list, of this doubly linked list, how about every time we do a get, we move it to the head of the list? So I'll just say move to head of list. Private void move to head. Okay. And how are we going to implement these? Well, we already have references, so I'm going to, at this point, add in let's see, a node head and a node tail. Rather than dealing with like a null terminating list, we're going to have a head and a tail node on each end of our list. So at the very beginning, let's see, I'll just say head dot right equals tail, tail dot left equals head, just to ensure they're pointing to each other. So when we add a node, we're going to be adding it to the first, so we need a reference to whatever the node after that is. So node second. Actually, let's see here. When we add a node, we just need to say, okay, the node's left just needs to be the head, and the node's right needs to be whatever the head dot right is. And then we also need to update the head. So the head dot right dot left equals node, and then head dot right equals node. So these two are just fixing the node pointers, and these two are fixing the ones pointing to the node. If this doesn't make sense, I'll actually, you know what, I'll draw this. All these linked list questions are really annoying to me unless I draw them out. So we have our head and our tail already pointing to each other. When we add a node, what are we doing? So we have our new node, and we see in our code we're adding node.left equals head and node.right equals head.right. So node.left equals head, node.right equals head.right. So we're looking at head.right, and then head.right.left, this arrow right here, that's going to equal node, and then head.right equals node. So that, all that's doing is really inserting, just changing 4 pointers. Okay, back to the code. Okay, similarly, remove node, we're also going to have to remove 4 pointers. So what would that look like? So I'll draw it out too. So for remove, we'll have some node. I'll just call it pre and post. And then we'll have a pointer to this. This is our node. So what are we doing? So we're just saying, okay, we need to just change these 2 arrows. We need to change this arrow to this, and to change this arrow to this. And then also probably remove these. So what's that going to look like? We need references, so node, I'll call pre it equals node.left. Node post equals node.right. And then we just need to update these 2. So pre.right equals post, and post.left equals pre. So that's just a delete. And then what is this function? This is the move to head of list. So that really just is a delete and an add, which we've handily done already. So delete or remove node, and add node. So that's pretty clean. So we have our linked list, or doubly linked list implementation. Let's go for the rest of it. So what did we say earlier? We needed a map, not of integer, not of key to value, but of key to node. Why isn't it like that? cap equals new hash map. And then also a capacity is 0. I'm going to make these, I'll keep them public, I don't care. Our capacity and then our counts. This is just the amount of items currently in the list. Head, tail. Cool. All right, so let's initialize some variables. I guess I'll actually do this a little better. So, you know, this dot capacity equals capacity. Let's see, I didn't actually initialize head either, so head equals new node, tail equals new node. Okay, so now all we have to do is the get and puts. Connect those to our linked list somehow. So should we do get or put first? Let's do get. So right off the bat, we need to figure out what, for get, we need to figure out if it exists. So node equals map.get at key. Two cases. In the case, let's see, if it doesn't exist, we're supposed to return -1. So it's node equals null, return -1. Otherwise, what are we doing? We're just going to return the value. So node dot, come on, whatever, val. And we also need to update, we need to use move to head to update it. So we'll just call this dot move to head node. And so yeah, it's pretty clean. The solution happens to work out very nicely. So what are we doing for our put? So again, we have to see whether this is a insert or an update, because this changes things. So again, we'll say node equals map.get hash key. So what are our cases? So if node equals null, what does that mean? That means an add. It's an add. I'll say else. It's an update. In the update, that's simpler. We'll do that really quickly. That just means our node.value equals value. And then we have to move it to head like we did, because that counts as a use. Like any get or put counts as a use. So this dot move to head node. Okay, and then in our add case, so what is this? So if we're adding in a new item, then we'll need a new node. So node equals new node equals new node. What are we doing? So new node dot, say key equals key, new node. And then our left and right. So yeah, so and then we just have to put this in there. So what was the function name? Add something. This dot add node. We should deal with our count and capacity. So count plus our capacity, or I guess our capacity stays the same. Oh, we didn't actually add the value, so to our map. So really, our map dot put key node, increase our count, and then we need to decide. We need to decide whether to boot a node if we're over capacity. So that happens if the count is greater than the capacity. So first of all, count minus minus, and then we're just going to delete, let's say this dot, what did I call it? Remove node, and then we also need to remove from the map. Let's see, map dot remove, and then key. And that should be it. I'm just gonna double check some stuff. Creator item, we initialize all our fields, our linked list, and our map. I will change this. On our get, what are we doing? We are trying to get, and on successful, we update our list and return the val. We don't update anything. Good. And then on our put, we get the node. If it's an update, we just update the value and update the recently used status. Otherwise, we add a new node into the map and the linked list, and then potentially remove the least recently used entry. Let's see if it compiles. Null pointer exception. Let's see. Line 71. Node dot left equals head. I wonder what test case was this for? What's going on here? Probably node is null. Or yeah. Let me debug this and see what's happening. Yeah, there's doesn't really tell us much right here. Why would add node be null? So add node is called right here. Oh, wait. Okay, yeah, this is node is like in case we didn't get it, we really should be calling it I'm just going to update it actually. I'm going to say node equals here. Actually, I'm not. I'm going to stick with it like that. That, new node. Oh, and then this is wrong too. Right here, we're adding it in, the new node, and then we're trying to figure out what to delete. And we shouldn't be removing what we just added in. We should actually be removing potentially the really the item at the very end of the list, because we're always inserting and updating at the beginning of the list. We should remove the last one. So something like this dot tail dot let's see, we need a reference too, so equals and I think we need a new we might need a new method too. We need a method to remove the last item of the list. Which I'll write down here. And I'll say, we can call this like something like pop tail. We'll return a node result equals tail dot left. We have to remove it. Okay, so that should get us, that should just pop and remove the last item in the list. And that should give us, so right here we should be saying this dot pop tail. And we're not going to move that, we're going to move tail.key. And that should be right. Famous last words. But I think that's right. So let's see how that works. So it looks like it passed the initial basic text case and also everything else. Good old Java. All right, so that was least recently used cache. See you next time.